Hi, welcome back. We're in Engineering 11. This is MATLAB. It's Monday morning, I suppose, the 27th of 2020. This is January. Thank you, Michelle, for reminding me where and when I am. Today we're going to be talking about Lesson 3, at least in the lecture portion. We're going to be doing a mix of actually handwritten analysis as well as some MATLAB code. Those of you that are following along at home and in person, I would highly encourage you to get out your MATLAB full screen command prompt so we can get that running. As a friendly reminder, am I not?
Yeah, you're not.
It looks like on my side the thing is on streaming, but that doesn't necessarily mean that I'm live, as I learned last week.
Yeah, you got to start it in Notepad.
I did.
Okay.
Yeah, I'm not sure what's going on there. Yeah, you see me? Okay. So, and how's the sound? Can someone hear the sound? Yeah, I'm gonna get better at this, I promise. Maybe we'll go down this way so you can see my silly face, my silly old face. I mean, young face. I'm gonna really talk positively for myself here. All right, so this is gonna be Lesson 3, Unsigned Ints, Integers, and this is what we call storing and manipulating. Unsigned integers in MATLAB. I am still working on my systems. If you all have suggestions on how I can make this better for you, you let me know. I'm so open to the concept of not sucking. So let me ask you this. Do you remember the 1st of November? Do you remember how many data classes MATLAB has? Off the top of your head? So recall, yeah, MATLAB has a total of 16 quote-unquote native data classes with, for us, the capacity to add more. So if we wanted to, we could very easily write our own data classes, and in fact, in one of the labs, we're going to write what I call an unsigned fixed point data format, which we'll talk more about. As a friendly reminder, as we begin this, I want to go to the specific MATLAB documentation that helps me capture this. If I wanted to understand where the documentation for the for the data classes in MATLAB were, what would I do? Yeah, we're gonna at break time, Misha, I'm gonna have you and I are gonna work on this together so I can see it because it's not capturing this. Do you remember where the data class documentation was in MATLAB? Yeah, that's true. It is in documentation. So I'd like you to find the introduction to MATLAB data classes. One thing that we could try. And I want to kind of pose, I was so proud of you all last week, by the way. I learned a lot. I learned control period kills. I learned make dir, move dir. And there were some other, so if you do the plot and you don't put the little line there, it puts the little, yeah. Those are all things that you all taught me. Many of those things I knew in my past. So here's a question for you. If I wanted to go from the command window to the 16 data class file, anybody know what command I would write in? I'm guessing, yeah, there they are. So if I put help classes, I guess it said help class. So let's go ahead and see. Can you see that? Yeah, there it is. So if I'm looking at this thing, we're going to have what we call double, single. Anybody know how many bits is allocated for a double precision floating point integer? 64. Single, half of 64? Could you guess extended? It's not in this necessarily at this moment, but could you guess what? Yeah, twice a double, right? So extended precision is twice a double. We have a logical array, a char or a character, cell, which we'll talk about much, or structure. Today, we're going to focus on the integer classes. So do you see those integer classes? int 8, uint 8, int 16, uint 16, int 32, uint 32, int 64, uint 64? For lesson 3 and 4, we're really going to get into that. Could you guess what the difference between an int and a uint is? Yeah, Misha.
It saves one bit at the front for sign. Should be positive or negative.
So if it just says int, we're thinking signed integer. What's another way to say a signed integer? It could be positive or negative. On the other hand, uint might be unsigned integer. So doesn't have a sign, meaning what's another way to say an unsigned integer? Say it again. Non-negative. What's the difference between positive and non-negative? Meh. Oh, sorry. Yeah, it includes 0, right? Mathematicians are kind of funny that way. All right. So I want to kind of take a look at the following idea. This is a graphical representation of the same concept. So we have logical, characters, numeric. All of these are numeric. We have two types of numeric, which we're going to talk about today. We have what we call integer numeric and fractional. Oh, so sorry. That's kind of interesting. Okay, and I definitely don't want to feel drunk. At least if I haven't earned it, right? So we have what we call two things. We have integer numeric and fractional numeric. I'm going to actually say that in fractional numeric, there's an unclassified data class that is non-native to MATLAB, which is what we call fixed point numbers. And we're going to actually build floating point numbers on top of fixed point numbers. And what's crazy about this is we're going to build fixed point numbers on top of signed integers. Can someone guess what I'm about to say next? Unsigned integers. So the entire concept of storing numbers in a computer, the base layer of that is to understand very, very well what? First unsigned integers, and then no, sorry. First sign, then first unsigned, then signed, then fixed point, then floating point. Okay, so now just go ahead and count up from lesson 3. Lesson 3, lesson 4, lesson 5, lesson 6, and 7. And that's because floating point numbers are actually not trivial. There's a lot going on there. And then what that will allow us to do is we will have a full conceptualization of everything happening in the numeric variables. Someday when I grow up and I don't suck, I'm going to get to a place where we as a team will actually study all the 16 native data classes, and then eventually when we do a little bit more complex ideas, you'll create like 2 or 3 other data classes that are useful for some project. By the end of this quarter, I will be very satisfied if we can really get our heads around these, with the hope that you'll have an unfair advantage when you actually go to code in MATLAB in your future. I do want to go ahead and give a standard call out. In the documentation having to do with the classes, there's a lot more information about this. We will break this down as a team. So in this case, single and double are both what we call floating point numbers. All of these 8 data classes are integers, and then characters and strings are kind of grouped together. We'll talk more about this as time goes on. How many of you remember reading this article for your lab 2? Awesome. Very cool, right? It's almost like I'm useless. That's exciting. Instead of writing this all down for you, what I'm going to do is kind of orate it You have this captured, and you could write it for yourself, but the nice thing is the fact that this is on YouTube and the notes are posted online means that we could do this as a team. I would always recommend that anything you see I've written, you rewrite that thing for yourself. We'll talk more about that as the day goes on. I want to talk about what I would call math-specific number systems. Could you guess what I mean by math-specific number systems? Mechanisms to describe numbers in math classes. What I'm about to say is not directly relevant for computer science classes. Could you guess why? All computer scientists are mathematicians. Not all mathematicians are computer scientists, right? All engineers and scientists are mathematicians. Not all mathematicians are engineers and scientists, right? This is really used for theoretical math purposes. I want to set the foundation so that we can refer back to these sets, and then we'll make a direct correlation between what's happening in math and what's happening in MATLAB. So the first and most famous number set that we're going to study is something called the natural numbers. Yeah, anybody have French citizenship? And some of my Chinese students said that they do this in China too. Anybody have French or Chinese citizenship? If you have French or Chinese citizenship, you are allowed to include 0 in the natural numbers. Otherwise, we start at 1. Yeah, that's a true statement. I had French mathematicians who yelled.
Your primary understanding of numbers comes from computer science?
Yeah, I have a lot. I actually want to, before I die, I'd like to introduce a notation and have it adopted by the greater mathematical community, which maybe we call like n naught, which is the natural numbers including 0, just because that set is so special. I've also thought about calling this like Z0 or something like that, which all the integers starting at 0 and Z positive 0 was another way that I thought about this. This one is my favorite one though, right? But for us, when we say the natural numbers, it's all positive integers, not including 0, right?
You mean
No, I mean positive. Yeah, this is where American mathematicians should be slapped on the wrist with a solid effort. Okay, so could you guess what I'm about to say next? What's the next number system that we're going to study? Whole numbers, which includes both positive, negative, and 0. In this class, for natural numbers, if you wanted to say n sub 0 was all natural numbers including 0, I think I would be very, very proud and smile in my heart and my face. Okay, so we've got natural numbers, we've got integers. Can you guess what I'm going to say next? Yep, rational numbers. And the way that I love to think about rational numbers, maybe we should zoom in a little bit so this isn't too overwhelming. I'm going to highlight something for you. What does that say? Ratio. What's another way to say ratio? What's a synonym for ratio? Fractions. And what's really, really cool about ratios, or what we call rational numbers, is that we can write every rational number as a fraction involving what? Integer divided by integer, right? Every rational number we can write with an integer in the numerator and an integer in the denominator. And really, this is well beyond the scope of this class, and it really should have prerequisites. But what we really say is that every rational number is actually an equivalence class. So there are an infinite number of, for each rational number, there are an infinite number of unique ways to represent that, right? Kind of get this idea? So we'll talk more about that. Okay, so let's go through them. What's the first set that we're going to study? Natural numbers, which are, damn, Michelle, positive numbers, unless you're French, in which case that includes 0. Right. What's next? Integers, which are positive negative, and 0, right? And then rational numbers, what are rational numbers again? First 5 letters of the word rational, ratios of integers. Ratios of integers, right? And in fact, the set theoretic definition, if we see this, the set of rational numbers, and you'll notice that these are really special. This is called blackboard lettering. Blackboard lettering has these extra special second pieces. So it's not just Z, it's Z with 2 bars. It's not just N, it's N with 2 bars. That's called blackboard lettering. I'm going to say this right now. If you write N without the blackboard lettering, in my mind, I do not read the natural numbers. I read capital N, and I'm thinking it's either a matrix dimension or some integer, right? These symbols represent hope in the city of Gotham. They're very, very special, right? Okay, so the rational numbers is the set of all P divided by Q such that P and Q are integers and Q does not equal to 0. And then this end brace in this notation is an unpronounced. It's like a period, right? When we use the English grammar period, we don't actually say period out loud, but it lets the user know end of statement. So this is what we call set notation. Okay. Could you guess what happens above and beyond rational numbers? What's the next set? Real numbers. And then for people excited about life and math, if you want to know what the real numbers are, take a real analysis class. In my life, I've taken 6 real analysis classes, not including other classes that really should be categorized as real analysis. 2 years of my life, probably over 2,000 hours studying this. These things can be constructed, but because anybody want to give me 2,000 hours over the next 8 weeks? Okay. Yeah, I didn't think so. So what we're going to do is do something that's completely mathematically ridiculous, but unless you're willing to give me 2,000 hours, then don't argue, right? Here it is. The set of real numbers, what's that thing called? Yep. The set of real numbers, that's how we read that out loud, is equal to the set of all x such that x is a real number. If you want to know what it is really equal to, take that real analysis class and suffer for 2,000 hours, and then you'll be like, Jeff, that was really cheating. Okay, so we've got natural numbers, we've got integers, we've got rational numbers, we've got real numbers. Anybody guess what the next set is?
Transcendental numbers.
Actually, transcendental numbers are included in the real numbers.
Imaginary?
Yeah, imaginary. What's another way to say imaginary?
Irrational.
Irrational actually are real, so those are different. Imaginary and irrational are not the same thing. But I love the guess. Beautiful guess. Complex numbers, right? And complex numbers, in this case, we use Blackboard C. The complex numbers are the set of all a plus bi, where a and b are real numbers, and I is the square root of -1. There's a whole other class called complex analysis. I've taken 3 upper division and graduate level classes in that subject. Really, really beautiful subject, useful in electrical and mechanical engineering and other places as well, differential equations really. Okay, so let me go ahead and say this. So number sets in a visual. What is the smallest set of numbers that we just discussed today? What has the least number of elements? Natural numbers. Okay, so we're going to say that the set of all natural numbers, which set is slightly larger, definitely includes the natural numbers, but not much more. Integers. So in other words, I guess we could write this in math symbols, right? So we say the natural numbers are a subset of the integers, but they definitely the integers include more than just the natural numbers, there's no possibility of them being equal, right? So this subset notation, if I put a little line under it, it would say, oh, the natural numbers could be completely equal to the integers. Is that true? Prove to me right now that for sure the natural numbers are not equal to the integers.
Zero.
0, thank you. 0. What did Misha just say? For sure, 0 is not in the American national numbers. Therefore, there exists a number in this one that's not in that one. Therefore, indeed, the natural numbers is strictly contained within the integers. Wouldn't it be nice if Math 22 was a prerequisite for this class? That would be called intelligence by design, right? But it's a nice review. Okay, what's next? Jean? Jean? What's next? Or Jessica?
Is there one between that and complex?
Yeah, there's actually, I think, 2.
Oh.
Yeah. Starts with an R, ends with an atio.
Rational?
Yeah, there you go, rational. Okay, so we're going to say that the rational for sure includes the integers. How do I know that the integers are included in the rational? Denominator equal to 1. I can write all integers as a rational by just dropping a 1 in the denominator, right? So this is the pictorial representation, which you might call a Venn diagram. The symbolic representation, so we'll call this for those of you that know my concept of concept images versus concept definitions, we'll call this a visual representation. And we'll call this thing down here a symbolic representation. Both are useful, and in fact there's brain science to say the more ways you can think about something, the more neural networks and connections you create. What's next here? And I might go back to Jessica. So we've got natural numbers, integers, rational numbers. And then you at one point said complex numbers. And that is the Roman Empire of the number system, right? It's subsumed. Maybe we call it the Mongolian Empire, or I don't know.
Excluding real numbers.
Yep. So the one in between we call the real numbers. And the reason that we say all real numbers are definitely complex, if we think about complex numbers as a plus bi, set b to 0, and you get back into the reals. The chain of inequalities, or what we might say subset inclusions, rational numbers are included in the real numbers, and real numbers are included in the complex numbers. But for sure there's stuff in the complex, not in the real. What's in the complex and not in the real? At least one, right? What's in the real and not in the rational? Pi is a really fun one. E is another fun one. Should we do something crazy? E plus pi. Stop. Pi squared. Square root of 2. Yeah, okay, stop. This is what we call transcendental, by the way. Rational, what's in the rational that's not in the integers? 1/2, for example. What's in the integers that's not in the natural numbers? 0 and anything negative, right? Yeah. Okay, so we're going to start with some idea of trying to represent these numbers within a computer architecture structure. And this problem really goes back to the ancient times. One thing that we recognized way back when is that doing arithmetic in your head is hard. So could you imagine what people used to dream of? Instead of having to do arithmetic in your head, design something that does arithmetic outside your head. So there's something called an abacus. That was an early representation. There's a guy in the 1800s, a girl too, Ada Lovelace and Babbage, who created an actual mechanical representation of this. So today what we're going to do, today and for the next few days, let's really, and I don't know, we're all adults here, right? Get intimate with numbers in ways that maybe you've never have. Hopefully are new to you. All right. So the first thing that I want to talk about is something called the decimal number system. So let's focus on n sub 0. What was n sub 0 again? Yeah, the non-negative natural numbers. I will advocate that the entire mathematical community take this quite seriously. Introducing this is so useful for computer scientists, and since mathematicians serve client disciplines, we should take those client disciplines as seriously as we take ourselves, right? So we're going to call these the non-negative natural numbers. You all don't know this about me, but maybe you're starting to know this about me. Sometimes I call myself compulsive, and I have a student this quarter saying that you shouldn't call yourself compulsive. You should call yourself fastidious. Okay, I'm fastidious. That's awesome. One of the habits that I get into when I make notes is that I like to timestamp my work so that 5 years from now, when I come back to this work, I know exactly where I am. I also like to do page numbers. I would encourage all of you to do the same, and you'll see me kind of work on this. Okay, so we're going to focus on the non-negative natural numbers, and let's investigate the decimal system. I need a quick reminder. Deci, what the heck does that mean? Something about 10. That was one of the most articulate and concise sentences I've heard this morning. Very nicely done, Nick. Something about the number 10. Okay, so we're going to say, and I want to say this, could you guess why we like deci? Yeah, that's true.
The knuckles on one of our hands.
Yep.
Our four fingers is baseball. So.
We have 10 fingers. And I'm going to say this right now, counting with your fingers is a very sophisticated thing to do. I know that people rag on it, but I love counting with my fingers. And when things get really big, I have to take off my socks. Right? Okay, in base 10 decimal number system, we can represent any, right now, why don't we call it lowercase n in n? Can someone remind me what the heck I mean by this?
All n
Some
is number.
non-negative natural number as a quote-unquote string of what we're going to call decimal digits. And this literally comes from the Latin word digitus, which means finger. It's funny because it's true. So we're going to say with n, and why don't we call this, this one's actually, I kind of forget how to do this at the moment. With each digit chosen from the set, I like to call this set D. I am currently in the market for better notation. So you don't know this, but I'm writing a textbook in math in MATLAB right now because all the other textbooks that I've seen teach syntax, and my opinion is, if you want to teach syntax, you should teach them how to read the freaking documentation. Really, if you're going to teach MATLAB well, you should teach the underpinning, and then let students figure out what to do on top of that. I love it when my students make my textbooks better. So if you have notation suggestions that you think are more beautiful than the ones I've chosen, come talk with me. Notation matters. Big time. In fact, if Newton would have had access to Leibniz notation, Newton's work would have been accelerated by years, right? This is one of the most undersold things that we talk about in math. When we discover and create great notation, it can simplify the struggle of learning by days, months, or years for a new student. We'll talk more about that as we get to know each other. Okay, so the whole concept, we're going to focus on what we call the non-negative integers. We're going to say that each non-negative integers can be written as a string of decimal digits. Each decimal digit is going to be chosen from the set D, which in this case is going to be the set of all digits 0, 1, 2, all the way to 9. Right? So let's take an example as a place to start. So here we go. Let's look at an example, and we'll call this example, I don't know, 3.1. I suppose today is Monday, 1/27/2020. And what time is it at the moment? 10:42. Oh my God, that last page took me only 4 minutes. Damn, I'm freaking flying. I think I deserve a raise. So at least I can pay rent in the Bay Area, right? Oh, income inequality. Have fun. All right. So let's look at the next one. So let's look at a 2 decimal digit number. And then I don't know, do you want to do the one in the actual notes that I put online, or you want to do a different one? You want to be exotic? Different one? All right. You know what I call that? Courage. That was really fun. Okay, so we need a 2 decimal digit number. Could someone give that to me?
Which one?
Give me your 2 decimal digit number. Wow, okay, that's kind of fun. 21. Okay, so I want to go ahead and label this. So let's count the number of digits. How many digits are there? Yeah, there are 2. We're going to actually count digits from right to left, which is pretty freaking stupid because we usually read from left to right. But you'll see why we do this in a bit. So we're going to call this digit 1, and we'll call this digit 2. What does that actually mean, 21? Yeah, it means 20 plus 1. Let's go ahead and write that in base 10. This is going to be 2 times 10 plus 1 times 1. Let's go ahead and write that in base 10 using powers. So this is 2 times 10 to the first plus 1 times 10 to the 0. These things right here have a special name, which we'll talk about in a second. In fact, this is the power associated with digit what? 1. Okay, if this is the power associated with digit 1, could you guess what we call this one right there? I like it when you label right there, right there. Thank you so much. I just saw 2 people smile. I think they were laughing at me, right? Not with me. You just keep laughing at me all you need, okay? When you laugh at me, my heart smiles. All right, so that's digit 2. We're going to actually call this position 1. Could you guess why we call that position 1? Yeah, we're going to make a connection between math and computer science. If we call this position 1 associated with digit 2, could you guess what we call this one? Position 0. Okay, so when we're tracking this, the first digit correlates with what? The 0th position. So full sentence, finish Finish my sentence for me.
The second digit correlates to
Position 1 correlates with digit 2. So let's go ahead and do this. Let's see our observations. What are our observations? The digit number increments. What does it mean to increment? Yeah. She didn't even have to say a word. She just went like this. That's called style. Goes up. Increments from left to right or right to left? Yeah. Right to left. And who says Americans can't read from right to left? Yeah, well, we're not sure if Americans can read numbers, but I think we can. Say it again.
If you read that, right to left, it says left to right.
That's confusing. That's awesome. You just made me smile. All right. So the digit number increments from right to left. What is the digit number count? Hard to say out loud, huh?
It's a multiplier to its assigned power.
Ooh, you're a little bit. You're 3 steps ahead of your teacher. 4 steps ahead of the class. Oh, sorry. Did I just serenade you with Aladdin? Yeah, I did. What is the digit number count? You're 3 steps ahead of your class still. You got to slow way down. What is the digit number count? What is each natural number in the decimal number system? A string of decimal digits. So each n element of the non-negative natural number is a quote-unquote string of decimal digits. And then the question is, well, what the hell is a decimal digit? Well, what is a decimal digit? Yep. So digit numbers count the... You're a little bit too fast for me, because those two concepts are actually separate. You're right, but you're just 5 steps ahead of me. What is a natural number in the decimal number system? A string of decimal digits. Say that again. A natural number in the decimal representation is a string of decimal digits. Well, what the heck is a decimal digit? A character between 0, 1, 2, all the way to 9. So first digit is going to be one of those. Second digit is going to be a different one of those. Third digit, etc. So what is the digit number count?
How do you mean the digit?
It's just not easy to represent, huh? Verbalize it. It's hard to say, isn't it? Maybe we should come back to this one because we need more examples, right? Okay, so digit numbers count the individual something. I might say decimal digits used to represent each non-negative number. Yeah, and then Michelle is super fast. I mean, all of you are super fast compared to me, right? What is the position number count? And why don't we just go ahead and track this? Position number, how does it increment? Does it increment left to right, or does it increment right to left? Right to left. In non-negative integers, we're going to come back to this later, the rightmost, oh God, digit corresponds to what? Position 0. Okay, so let's go ahead and have Michelle kind of lead us in the charge. Michelle, you were now ready to say position numbers do what? We'll come back to Taylor because you were the first one that. Do you see what we're going to do the next one?
Yeah, I see what you're saying. This is.
It's crazy. How many of you thought you understood the decimal digit system? And now I'm asking you to articulate it, and what do you notice? If you really know something well, claim you should be able to teach it to my 3-year-old. Right? If you really know something well and you get every idea of it, you should be able to articulate it to your grandmother, who's not a mathematician, right? And what are you noticing when I'm challenging you to say out loud something that you thought you knew? Anybody at a loss for words? Do you know what we call that? Learning. That's why I'm paid so much, right? Resentful much, Jeff? Yes. I'm resentful of every Facebook and Google employee who's outbidding us in the housing market. All right. Position numbers count the what? Do they count the decimal digit? Count the power of 10 that correlates to the corresponding scalar stored in that digit. And somebody that's taken Math 2B, I want you to say linear combination and coefficient. Each unsigned natural number is a linear combination of basis vectors. Each basis vector is a different power of 10, and the corresponding decimal digits are the coefficients associated with each of those powers of 10. Boom! Yeah, it's a dot product.
Whoa.
Yep.
Dot product to multiply two vectors, but the vectors aren't.
Yeah, we'll come back to that. We'll come back to that. We'll come back to that.
Yeah, it's one-dimensional.
Yep, there's a lot going on there. So now let me ask you this. What is the connection between digit number and position number? Notice, yeah, the digit number and position number are not identical. And as Jean said, oh God, they don't match, which is a way better way to say that, right?
Well, match for computer science, really start with 0.
Don't match. Yeah, you could call this digit 0, right?
Yeah, it's memory block 0, then you have memory block 1, then you have memory block 2.
Okay, so he's actually introducing this new idea that each of these things can be associated with a space in memory, which we'll talk about in a bit. Okay, so you're for sure true that digit number does not correlate with position number. That for sure is true. Is there a relationship between them? Okay, Nick, if you were just like 50, 70 years older, you'd be famous for the rest of time, right? Maybe 1,070 years older, but still. They are off by 1. Can you come up with a formula to relate them? Digit number equals what? Position number plus 1. And then one of you algebra specialists, I almost want to go to Art because I know that Art is now a professional algebraist. And I define professional as anybody that makes money doing something, and he is making money doing algebra. So if digit number is equal to position number plus 1, what is position number equal to? Yep. Minus 1. We don't have notation to do that yet. Whoa, who would have thought that we could spend 14 minutes on the number 21? Ask me how many minutes I've spent thinking about this particular topic. Should we do one more page and then call a break, or do you want a break now? I don't think I heard that. One more page?
Yeah.
Okay. I heard, I think, these two. So this is called Democracy by Two, not unlike.
Everybody else abstains.
It's democracy.
Yeah, we'll talk about this concept of universal voting. Anybody ever had jury duty?
No.
If you don't show up to jury duty, you get fined, right? There's a concept in somebody named E.J. Dionne in the Brookings Institution has this concept of universal voting. You must submit a ballot. You don't have to put anything on the ballot, but if you don't, you get the same fines as jury duty. I love that concept. I think I want to advocate for that concept to my local representatives. It's a good one. Okay, should we look at another example? Say yes. I'm not sure what's going on there. Let's do one that's more interesting. So let's do example 3.3, I suppose, this one. And we'll do a 5-digit number. And I kind of forget right now. I think this one might be something like 2 to the 15th. Let's see. I'm guessing most of you do not have this one memorized. So let's see. 2 to the 15th. No, it must be 2 to the 16th. Yeah, there it is. So what I want to do is set this equal to 2 to the 16th minus 1. And you're going to see when we talk about uint 16 why I chose this one. It's almost like I was setting myself up. Can someone tell me what that number is, please? 2 to the 16th minus 1? Yeah, so this is going to be 6, 5, 5, 3, 6. This is what we call a power representation. This is what we call a decimal digit representation, minus 1. Hardest problem we've solved today, 6, 5, 5, 3, 6 minus 1 is, of course, 6, 5, 5, 3, 5. Okay, so see if you can beat me to the punch. I'm going to start labeling this number. What are the two different labels we have? Bintang? Well, let's not waste the 14 minutes that we spent, right? It's almost like that 14 minutes directly relates to the next 14 minutes. Bintang? Sí se puede. Yes, you can. Como dijo Dolores Huerta, like Dolores Huerta said, sí se puede. When we label any number, a decimal representation, we can count both the and the position. Okay, so talk me through this, Bintang. What do you want to label first, positions or digits? Oh, I was just thinking the same thing. Okay, talk to me. What is the 5 there?
1.
Yep, we'll call that digit 1, and then nicely done.
Why call it digit 1? Call it digit 0. Oh, that's a position.
Yeah, well, I have to pretend that I'm a mathematician underneath, right? Actually, I don't. But I'm going to. Okay, we'll call that digit 1, digit 2. I'm not actually against calling that digit 0, except that it is useful to know how many digits you have in a number. And it's nice to be able to disassociate the count of digits from the position. So in particular, when we get to fractional representation, so for example, he just asked a question. So this was a very, very beautiful question. Why call the first digit number 1? Well, I'll tell you exactly why. 3.1415 digit 1, digit 2, digit 3, digit 4, digit 5. Yep. Position -4, -3, -2, -1, 1.
Oh,
Digits stored in memory, you can count the number of digits that are stored irrespective of their position.
okay.
So it is nice to be able to say digit 1 is the first digit stored in the least significant position regardless of the correlating position number. Later on in the course, we can actually debate that, but I do think that it's useful, and later as we get further into memory structures, that representation is quite useful. Beautiful question, by the way. Okay, what in unsigned integers, we said that digit 1 correlates to position 0, and we came up with this very famous formula. If we were only a few hundred years older, we would be famous. What was the formula if I wanted to go for unsigned integers from digit number to position number? Subtract 1. And I'm going to go ahead and say, like a good Catholic, we're going to use pain to our advantage. Da-da-ch. No joke? No. We need a break. Either that or I'm not funny, but I refuse to admit that. So. Okay, so we have this concept that this is going to be 5 digits representing 4 positions. Can somebody give me the inner product formulation of this concept? Another way to say this, could you break this number down as its representations base 10? So first we're going to have 60,000, then we're going to have 5,000, then we're going to have 500, then we're going to have 30, then we're going to have 5. What's another way to say 60,000? 6 times 10 to the 1, 2, 3, 4. No? Plus 5 times 10 to the 3 plus and then this is what we call candy for the observers. So I'm going to go ahead and just those of you that have taken Math 1C, Math 2B will recognize that as that inner product, right? Could you venture a guess how we might introduce, let's finish this idea fully, and then we'll take our break. So it's more than a page, but that's okay. Rookie mathematician, you know what a rookie mathematician does when she runs out of room on a page? She like scrams it over here, makes some stupid mistake. You know what a professional mathematician does when she runs out of room on a page? Gets a brand new sheet of paper. And don't trip. I'm making paper. I got more paper than you could ever use. Okay, so let's go ahead and think about this for a second. Each one of these, could you guess what we call each one of the scaling coefficients in this dot product? A decimal digit. The question is, should we represent the decimal digits based on the digit number What am I now doing? We just abstracted away from the specific into the general. This choice of representation for our number y assumes that we're going to we're going to count digit numbers based on the corresponding count of digit numbers that we did. Do you see a downside of that? What is the whole concept of each digit? Each digit represents a power of 10. This index represents digit numbers, but not positions. Wah, wah. Why are we sad about that? The whole point of decimal representations is to track positions, also known as orders of magnitude with powers of 10. So in particular, I would say no. Let us not use the index which counts the decimal digit. Could you guess what I would recommend instead? Yeah. For a general approach, another way to say this is notation for unsigned decimal representation. Index each digit based on the position number. Michelle, I swear to God, if you were born in like 1904 and then you came to age as an intellectual in like 1945, you would probably be a billionaire right now. But, I mean, not that we would necessarily think that's a great thing, but that concept is a major concept in computer science. We'll see that as we go along. So here we go. How would I say this number in general now? Well, the number was 6 times 10 to the 4 plus 5 times 10 to the 3 plus 5 times 10 to the 2 plus 3 times 10 to the 1 plus 5 times 10 to the 0. Okay, let's go ahead and think about this. What's the largest position number there? Position number, not digit. 4. So now we know that D4 is going to be 6. Plus what? D3 times 10 to the 3. What is D3 in that case? 5. Okay, see if you can finish this before me. Oh my God, you all are geniuses. Repeated failure and correction leads to genius. When we fail and make mistakes, our brain grows bigger. Okay. Let me ask you this. Which one of these would you least likely to mess up on? Would you least likely... Okay, let me say this. Imagine I'm about to pay you in cash this amount of money, and I'm going to drop a digit. Which digit would you like me to drop? You would like me to drop the one that has the least impact, the least significant digit, right?
Actually, D4 is not that materialistic.
So this is going to be a fun class. I know what you're going to say. It is already a fun class. Oh, you stop. You stop. This is what we call the least significant digit. In other words, if I were to pay you this amount of money in cash and I refuse to give you this one, you wouldn't be that upset, right? Because you're not losing much. But if I was going to pay you this amount of cash and I was like, you know what? I'm just not going to pay you the digit number 4. You might say to me, give me my money. In other words, this is not least significant. This is most significant. Okay, shall we take a break? All right, what time is it at this exact moment? 11:10. Can we be back at 11:20? All right, 11:20. We're going to conclude this part of the lecture, and we'll be back at around 11:20 a.m. to start part 2 of this particular day. See you there.